In the following question, we need to write a detailed mechanism for the following reactions. In the first reaction, we have a primary alcohol in an acidic solution where the acid is hydrobromide and the product is a tertiary alkyl bromide. As we can see, the positive center between the reactant and the product changes. We can randomly number the carbons 1, 2, 3, 4, 5. While in the product it's 1, 2, 3, 4, 5. So in the reactant, carbon number 5 is a positive center, while in the product it's carbon number 2. I guess that this is the same carbon since it was substituted. Clearly, a 1,2 alkyl rearrangement occurred, and as we know, rearrangements occur when a carbocation is obtained. This means that this reaction happened in an SN1 mechanism. However, there's a problem. The hydroxide in the alcohol is a relatively bad leaving group, while for SN1 to occur, the leaving group has to be good. In this case, since the solution is acidic, the hydroxide undergoes protonation. Therefore, in the first stage of a reaction, the hydroxide undergoes protonation, which converts a bad leaving group, the hydroxide, into this group, OH2+, which is a good leaving group. Following that, in the rate determining step, the OH2+ leaves as a water molecule to obtain the primary carbocation, which is highly unstable. As a result, it immediately undergoes 1,2-alkyl rearrangement, when one of the methyls attached to this carbon migrates to the carbocation, like so, to obtain the following carbocation, which is tertiary. And this carbocation undergoes a nucleophilic attack by the bromide, which is in the solution, and is the nucleophile, to obtain this product. Since this product is not chiral, only one product is obtained. In reaction number 2, we again can see a change in the structure of the alkyl between the reactant and the product. We can see a ring expansion when in the reactant we have a cyclobutane, while in the products we have a cyclopentane, meaning in this case again we undergo rearrangement, meaning in this reaction we also undergo rearrangement. And therefore the mechanism in this reaction is SN1. We'll first try to recognize the carbons in the reactant and in the products. We can guess that this carbon in the reactants is the same in the products over here, since in both materials it's highly substituted. So we'll call this carbon number 1 in both molecules. So here we'll have 2, 3, 4, 5, and we can assume that we will probably get a carbocation on carbon number 1. One of these bonds, which are connected to carbon number 2, will migrate to carbon number 1. So we'll say that over here in the product is carbon number 2, 3, 4, and 5. When we number the carbons in this way, it's probably that this bond in the reactants broke to give us that 5 is connected to 1, forming a carbocation on carbon number 2. Giving us a 1,2-alkyl rearrangement. So let's write the mechanism of this reaction. Again, we can see that the reactant is an alcohol, which has a bad leaving group, the hydroxide. So similar to the first reaction, we need to change the hydroxide into a good leaving group. So it first needs to undergo protonation. So our first stage would be protonation, giving us a good leaving group, OH2+, which will leave as a water molecule, to obtain this tertiary carbocation, which is stable. Again, the step in which the carbocation is created is the RDS, the rate determining step. And as we see, a tertiary carbocation is formed, which is stable, and we usually wouldn't expect a rearrangement to occur. However, since the ring tension of a cyclobutane is high, it will drive the 1,2-alkyl rearrangement, in which this bond would break and migrate to this carbon. Just for clarification, I'll number the carbons 1, 2, 3, 4, 5. To make it easier to see the change in the structure, I'll just shift the bond from here to here. So now we'll have this material after the rearrangement, where the number of the carbons is 1, 2, 3, 4, 5, which is the same. And since the bond here on carbon number 2 was broken, this carbon is missing its electrons and therefore it's a carbocation. Now we'll draw the structure as a cyclopentane as we usually do. I'll randomly decide that this carbon is 1, 2, 3, 4, 5. 2 methyls are attached to carbon number 1 and the carbocation is on number 2. In the next step, which is a quick step, the carbocation would be attacked by the nucleophile. Cl- attacks the carbocation, giving us the final product. Now let's look at the final reaction. We can see again that the reactant and the product are different. The positive centers are not on the same carbon. In the substrate, the positive center is primary, and the leaving group is attached to carbon number 3, while in the product we'll number the carbons as 1, 2, 3. We can see that the bromide is attached to carbon number 2, which is tertiary, meaning that this molecule underwent rearrangement, and therefore the mechanism again is SN1. Again, our substrate is an alcohol, meaning it has a bad leaving group, and we can see that the solution is acidic. Therefore, in this environment, we will first see a protonation of a hydroxide. So as we said, in the first step, the hydroxide group would undergo protonation, which will turn it into a good leaving group, giving us this intermediate, OH2+, which is a good leaving group. In the next step, which is the RDS of the reaction, this group would leave as the leaving group, giving us a primary carbocation. Which would immediately undergo a 1,2 hydride, in this case, rearrangement. A hydride which is attached to the neighboring carbon would migrate to the carbocation, giving a tertiary carbocation. So we'll get a tertiary carbocation, and the hydride which migrated is now attached to the original carbocation. And in the next step, the nucleophile attacks the carbocation, and we obtain our final product. You might have noticed that in each and one of the mechanisms, the rearrangement is described with a direct arrow. We are not using a bidirectional arrow, and this is because the product of a rearrangement is usually so stable that it's not reversible. Therefore, we use a unidirectional arrow.